Hello and welcome again to the STEMCstudio channel, and in particular to the STEMCstudio series on geometric algebra. In this video we are going to take a look at a new product for our geometric number called the contraction. Now we are getting tantalizingly close to having a geometric number that we can use to describe all sorts of physics problems, to describe rotations, reflections, the Lorentz Force Law in electromagnetism, a whole bunch of things. However, we still have two products to go. We have the contraction and we have the geometric product. Now, I've decided to deal with the contraction first for a number of reasons. One reason I would say is that I don't think the contraction is given enough attention in physics books. And I think it's one of the most sort of elegant ways of kind of complementing the exterior product. So I think we need to kind of like introduce it before we forget about it later on, having done the geometric product. Another reason is that it seems to be very important in describing the physics of a velocity-dependent force, and the classic example of that, of course, is the Lorentz force, where we have a force that is proportional to the spatial velocity of the particle. The amazing thing is that when you take the Lorentz force and you put it in its full space-time perspective, the treatment of it becomes even more elegant using the contraction. And the time part of the velocity, okay, which is really related to sort of the energy, also connects to the time part of the Faraday field, which is the generalization of the electromagnetic field, and that gets you to an understanding of where the electric field comes from. So we're going to see that. I'm going to do a series on space-time and electromagnetism from the perspective of space-time, and you'll see how that happens. But for now, what we're going to do is we're going to use the contraction in our two-dimensional system, and we will be able to model electromagnetism in 2D, which is something that you just can't do using the conventional Gibbs cross product, because that obviously doesn't work in 2D. Okay, so let's get on with it, and what we'll do is we'll walk through some theory, and then we'll go and implement the theory in our geometric number. And then at the end, we'll actually just kind of like take a look at some examples of the contraction, so you get a much better feel from it by actually seeing it in action. Okay, let's get started. So the intuition behind it is we take two multivectors. Let's call one the left-hand side and one the right-hand side. And the symbol we'll use for the contraction is this sort of double less than symbol. This happens to be something that we have available to us in our computing environment, which is STEMCstudio. And so this is a pretty useful symbol to actually use for the contraction. You'll see that some authors use a sort of something that looks more like a kind of a hook, but it's the same thing. Okay, so when we see left-hand side contracted with the right-hand side, what we should think of is that the left-hand side, in some sense, is being removed from the right-hand side. And that, of course, can only happen if the right-hand side contains the left-hand side. And if it doesn't contain it, then the answer we get is 0. Okay, so this will make more sense when we actually kind of like look at a few examples in a minute. Now, as I said, there is this intense use in physics where it appears in Lorentz Force Law. This is the three-dimensional version of the Lorentz Force Law, and clearly that only works in 3 dimensions because of the cross product. But if we replace B by something which is really a bit more natural, which is that B is really not a vector but a bivector, and we'll see how to do that, then we can change the magnetic part of the force to be this V contracted onto the magnetic field, the bivector magnetic field, and this takes V out of the magnetic field. And what you're left with is another vector, which is kind of rotated in the direction of B, and that gives you the magnetic field when we've scaled it by the charge. Okay, so this generalizes to space-time, and it's very elegant, and we'll see kind of like how that works later. Okay, let's take a look at some concrete examples. Okay, now obviously we have our multivector now, and so it contains both it contains scalars, it contains vectors, and it contains bivectors. So we're going to need to consider how this new operator, this contraction operator, works between different grades, different types of elements in our algebra. So let's take E1, the vector, basis vector E1, and take that out of E1, contract it onto E1. Well, the answer is 1. I think that should be fairly intuitive to you. Actually, what's happening here is when you do E1 taken out of E1, the answer is E1 dot E1. It's the scalar product of E1 with E1. So we must remember, that's where this sort of magic 1 came from. It actually came from the scalar product. And in fact, the scalar product, the contraction of a vector with a vector is actually just the scalar product. It happens to be the same, okay? But things start to differ when we talk about a vector being contracted with a bivector. So if we take E1 out of E2, well, intuitively, E2 doesn't contain any E1, so the answer is 0, as we kind of like intuitively said before. And also, we could remark that E1 dotted with E2 is 0. Okay, so that's the origin of this. Okay, now let's kind of like see where this starts to differ from the scalar product. If this were the scalar product, E1 scalared with a bivector would be 0, because you only get a result when the two elements, the left-hand side and the right-hand side, have the same grade. So here we're starting to deviate from the scalar product. And E1 taken out of E1 wedge E2, remember this is can be thought of as an oriented area. The answer is E2. So the way I think about this, and this is, it's completely accurate, but it's a rather nice, easy way to think about it, is that what you do is you scalar product this E1 with this E1, and then what's left is, just E2, because E1 dot E1 is 1, so you're left with 1 times E2, which is E2. Okay, let's see how that works if you do E1 contracted with E2 wedge E1. So I've reversed the order of E2 wedge E1. Well, the way I compute this is I say, okay, I've got an E1 over here. I need to rearrange this bivector so that the E1 is on the left-hand side. If I flip and put E1 here and E2 over here, this introduces a minus sign. So I remember that. I've got one minus sign, okay? And now I've got just the same expression that I have above. So the answer is E2. I have to remember that minus sign, so I get minus E2. Okay, so that's kind of how you do the computation in your head. You'll get to the point where you can just kind of like do these by looking at them, and you'll do them in your head. Okay, let's take a look at this one. Okay, now we don't have an obvious rule for how to do this, so we need a rule, and that rule is that we take the bivector on the left-hand side and we sort of factor it out into two parts, the E1 and the E2, and then we contract first with the right-hand factor, E2 taken out of this, and then we do it again for the other one. Okay, let's just kind of like see how that works. So E2 taken out of E1 wedge E2, to compute that I have to flip these two. So I got one minus sign, but then the E2 dot E2 is just 1, so I'm left with E1 on this side, and I've got and I'm remembering that there's a minus sign, and then E1 dot E1, E1 taken out of E1 is 1, so just remembering the minus sign, I get a value of minus 1. Okay. To complete our the implementation in our geometric number, we're going to also need to know what happens when you take a scalar, and I've indicated that by alpha, out of anything. So this could be a scalar, it could be a vector, or it could be a bivector. And the answer in that case is that we just get the scalar multiplied by what we had before. Okay. Now it's a bit different if we have some multivector on this side, on the left-hand side, and we take that out of a scalar. And the answer is always 0, if the grade of the left-hand side is greater than 0. In other words, if the left-hand side is not a scalar. If it is a scalar, then we get the same value as we have up here. It's a scalar times a scalar. Okay, but for all other cases, we get 0. And then the final thing I should add is that the usual distributive and scalar multiplication laws apply. Okay, so that allows us to combine contraction with addition and with scalar multiplication, just as we saw in previous videos when we were combining, say, the scalar product with addition. Okay, so to implement this, there's a lot to sort of remember. We can make a lot of mistakes. So what I like to do is I like to sort of tabulate what the result is going to be of a left contraction, right? So in this column here, I've got, this is what the left-hand side is, or rather its components. So this is the A component of the left-hand side. This is the X component of the left-hand side, big L for left-hand side, and Lx is the coefficient of E1, Ly is the coefficient of E2, and Lb, the B part of our multivector, is the coefficient of the bivector E1, E2. So here's the right-hand side, and what happens if we combine them? Well, a scalar taken out of a scalar by this rule is La times Ra, okay? Scalar taken out of anything else is just that thing multiplied by LA, so that should account for the top row quite easily. Okay, now let's do this row. We're taking the vector LXE1 out of various things. If we take it out of a scalar, that's this rule, so we get 0. If we take it out of RxE1, then we get Lx times Rx, and then E1 taken out of E1 is just 1. Okay, see how this works? So if we take E1 out of LXE1 out of RyE2, then we get nothing, because if you take E1 out of E2, you get nothing. That's this rule here. Okay, and then finally, if you take LXE1 out of RbE1 wedge E2, then we get LXRB, that's the coefficient, and now the vector that we get is E2 because E1 taken out of E1 wedge E2 is E2. And so you might just want to check that the table is correct. Okay. Now, just taking a look at this table, you'll see that this main diagonal, these are all of the scalar contributions to the result, right? Everything else has got some basis vector in it. And these ones are the scalar contributions. You can see that the contribution to the E1 result comes from these two entries, and the E2 part comes from these two entries, and the bivector part is just this single entry. Okay, so we are going to be able to take this and apply it to directly implement it in our multivector, and we'll keep an eye on this table as we go. Okay, now there's something also called the right contraction, which is basically the same thing, but the symbol points to the right. And, the easiest way to think about this, I think, is just to kind of like imagine putting a sort of a vertical mirror up and you swapping over the left and the right. So it works kind of just exactly the same, but now you're pulling something out on the right. There is a relationship between the right contraction and the left contraction, and it involves certain sign changes that depend upon the grades of the things that are involved. But it's sometimes nice to have the right contraction. As a sort of a way to kind of like simplify formulae. I am not going to implement the right contraction, but I'm actually going to leave that as an exercise for you. I will actually implement it in this class just for completeness, but I'm not going to cover it in the video. Instead, I'm going to implement the left contraction. Okay, so let's do that. Let's go to our code. So we'll show our editors. I'm going to keep the code here. What we want to do is we want to create a contraction of two multivectors. So I'm going to create a multivector that I'll call A and one I'll call B, just so that we can kind of play with this. And here's A. Okay, and then the same for B. And we'll just look at the output that we produce as we do this. And then we're going to do A contracted with B is A taken out of B. A contracted with B, A taken out of B. Okay, so there we go. And there's no C arrow here, so no point in trying to render anything there. We're going to be dealing with, vectors, scalars, all sorts of things. So let's just run that. Let's see if we have sort of captured the idea. Yeah, there we go. So let's start playing with a few things. Something is not quite right. Oh, so A taken out of B is equal to, or evaluates to, whatever. And we get an answer 0 again because we haven't actually implemented A taken out of B. Okay, so you will remember, or you may recall, that I typically first implement a method that represents the operator before I actually do the operator itself, and then I implement in terms of that. That is for a reason that will become apparent a little bit later, but suffice to say that for right now we're going to create a method called LCO, and that stands for left contraction, and that's going to be our method that implements the left contraction. Okay, so we'll see down here that it's telling us LCO is not a function, it's not been implemented. So let's go over to our multivector, which is in the E2GA class now. Recall that stands for Euclidean two-dimensional geometric algebra. Here's our geometric number, and we need an LCO method. Okay, so we can grab anything that kind of like looks like it, and I think what I'm going to do is I'm going to grab this one. Okay, and an appropriate place to put it, if we want to stay nice and alphabetically ordered, is right there. Okay, let's try and implement it. Now, here's our table for the contraction, and I will just hide the output for the time being so that we get a little bit more, so we get the full table. I'm also just going to hide the Explorer over there. So let's implement the left contraction. So it's going to help, I think, if we make our implementation here look a lot like the code over here. So the way I'm going to do that is I'm going to define a constant LA, which is this dot A. Okay, so all I'm going to do here is I'm going to, and I'm going to, for example, do RA equals the right-hand side dot A. Okay, and then what I can do is, so for example, this diagonal is the scalar part. I can do something like this. I can say const scalar part equals LA times RA, and I can now just sort of read off from my table all of the contributions to the scalar part, which is the diagonal, and I put my result in there. Okay, and all I then have to do is kind of like complete this. It's not going to take us too long to do, so let's actually do that. So we'll need LA, LX, LY, LB, and this is going to be this dot X, this dot Y, and this dot B. And then similarly, we're going to want to have 3 more here for Rx, Ry, Rb, and then this is right-hand side dot X, y, and b. Okay, so I'm going to do a little desk checking here because we haven't got our automated testing yet. So let's just make sure ax, yb, ax, yb, ax, yb, ax, yb. Okay, so now we can complete our implementation. So the scalar part is LARA plus LX times RX plus LY times RY plus, or rather minus, LB times RB. Okay, so that was the, in some senses, is the most complicated, the longest expression to do. Let's now do the x component. So constant x is equal to, so what we're looking for is the E1 terms, and we see LARX and LYRB with a minus sign. So it's LA times RX, LA times RX minus LY times RB. Okay, and we slot that in to the x component. Const y equals, now the y part from our table, we're looking for the E2 part, so we're going to have an LARY, LA times RY, and the other one is plus LX RB, LX times RB. Okay, and we slot that into the y part. Okay, so we are almost there. Now, do note these sign differences. It's rather sort of subtle and not so obvious. Like why is this minus? Why is this plus? Well, that just is the way that the algebra worked out. But these are really critical, and it's easy to make a mistake on those. So just pay attention to that. Okay, so the final bit is, what do we get for the bivector part? And it's the, here it is, it's LARB. Okay, so const b equals LA times RB. Put that in, and we should be good to go. So let's kind of like give it a few little tests and just kind of like check our intuition. In fact, I'm going to get rid of the documentation because I don't really need it. Okay, let's try, bring back Explorer. Let's try some different examples. So let's go for some vectors first. So we'll just make this both the 0 vector, and then let's do EX taken out of EX. Okay, so E1 taken out of E1, and the answer is 1. So that's good. Okay, let's try EX taken out of EY. And so EX, and the, sorry, E1 taken out of E2, and the answer is 0. So that's kind of correct. Let's try E1 taken out of E1 wedge E2. Okay, and the answer is E2. So E1 taken out of E1 wedge E2, the two E1s, scalar product is 1. We're left with E2. There's the answer, E2. Okay, let's try some of the sort of reverse ones. So we can do a bivector taken out of a vector, 0. Okay, correct. Taken out of E2, 0. Let's taken out of itself, and we get -1. Okay, that's correct, because if you imagine, the process of doing the calculation, we've got E1 wedge E2 taken out of E1 wedge E2. We have to reverse the right-hand term so that we can get the E2s together. Okay, so that's a minus sign. And then we first remove the E2, so that's got a scalar product of 1. Now we have left with E1 taken out of E1 and still a minus sign. That's a 1, and then there's the minus. Okay, so this kind of basically seems to work. We can even, do some, take a look at a few examples that I think are kind of rather interesting. So what happens, and I think I'm going to look at the examples where we take out a vector out of a bivector. So if we take E1 out of the plane, the bivector, we get E2. So E1 taken out of the plane gives us E2. It's actually like rotating E1 in the direction of E2. I'm trying to build up the intuition here. So that's what's kind of like going on. If I had a different sign for my bivector, so if I had a minus sign in here, then the result is minus E2. So the bivector I'm taking it out of is rotating now to the right. And if I take E1 out of it, then the result is minus E2. As you can see here, minus E2, and that is downwards, okay? So contraction, when you have a vector being taken out of a bivector, can be thought of the vector being, firstly, it's being projected onto the plane, but we don't really see that because we're working in the plane. So E1 is already projected directly onto the plane. That's a generalization for 3D. But then the next action that we have to consider is we rotate E1 by 90 degrees in the direction of the bivector. Now, something else you also should just be kind of like careful of is that the result is going to be scaled by both the original vector. So let's take it out of, just to be a little simple, take it out of 1. So it's going to be proportional to the original vector size magnitude. So as we increase that, it scales up. And it's going to be proportional to the bivector magnitude. Okay. So here, if you take 2E1 out of 3E1E2, you actually get 6E2. Okay. So the way to think about this is that the 2E1 gets rotated in a direction of E1, E2, and then it gets scaled, increased by 3, giving 6E2. Okay, so there's the whole intuition for the contraction. So now that we have our method for the left contraction implemented, now what we want to do is we want to provide the operator overloading version of this so that we can do the same thing but directly with operators. Okay, and this will make our mathematics look much more natural. It'll make this thing look like our very general Lorentz Force Law, if that's what we happen to be modeling. So we go and take a look at the documentation for the contraction. And some of you might already recognize, okay, where am I going here? Operator overloading. That the symbol that we're working with for left contraction, this 2 arrows going to the left, is what we call the left shift symbol, normally when we're doing bit shifting in our language. And so that's why the dunder method is called _L shift. Okay, and then another double underscore. And again, there is a right left shift version. Okay, I hope that's not too confusing, but it's this is a variant of L shift that we can use, and we'll use that later if we want to generalize this this operator to work with different things on the left and the right hand side, maybe a pure number as opposed to a geometric number. Okay, so what we need to do is implement _L shift. Go back to our code, we'll open it up, and we will go to our multivector, and that's in E2GA. And let's implement the L shift. So this is going to look a lot like, say, this one, because it's just a binary operator, and LM, so we need to put it up here, L shift. Okay, so L shift is going to be the implementation of contraction, left contraction, and so we need it to call our existing method, which is LCO. And that should do it. So let's go and run our code. We'll hide that. Take a look at the output here, and it seems to be good. So it seems that we're we're getting the right behavior. Let's just check that. So we can do 2 taken out of 3. So E2 taken out of, 2E1 taken out of 3E1, or 2E1 contracted onto 3E1 is 6. And so that concludes it for the left contraction. We're going to find this super useful when we consider things like the Lorentz Force Law, and we'll be able to simulate the Lorentz Force Law in 2 dimensions, which is something that typically is not done. But it will help build our intuition for how the Lorentz Force Law works in 3 dimensions. And you can also see that the left contraction is also a rather nice way of factoring a bivector, at least in 2 dimensions, pulling out one part and saying, okay, what's left? So for example, you might be in a situation where you have an angular momentum, which would be described by a bivector, and you may want to know what is the force on the end of some moment arm. Well, one way of doing that would be to contract out the moment arm, and then you'd be left with the force. Okay, I hope you enjoyed that. If you did, well done for staying with the program, because this is probably one of the harder things to get your mind around. It's quite new to most people. And if you did like this, please hit the like buttons. That will help other people to find the video. And if you want to see the next video in the series, hit the subscribe button too below, and we will move on to what I think is like the holy grail of geometric algebra, which is the geometric product. It's going to be our final product. And then beyond that, we'll have a few episodes where we'll add some polish to our geometric number. We'll introduce some testing. We'll improve our printing output, just to make that a little bit more elegant, and any other kind of finishing touches we can kind of like think of, and then we'll be ready to really use it in applications. Okay, take care. Enjoy doing the right contraction, and I will see you in the next video. Take care and happy coding.